evidence for this dependence in scattering rate inescapable? Is
So,
it anisotropy in the directions, or?
So the anisotropy is one piece of evidence that goes in this direction, but for the solar system data in particular, there's a huge amount of data of almost every species that is any kind of secondary, basically. So, the biggest thing, the simplest thing people usually use is some different versions of a secondary to primary ratio, boron to carbon, positron to electron, antiproton to proton. Things that are basically created on the fly by the cosmic rays hitting ISM atoms or nuclei to the ones that are accelerated with the cosmic rays. And every single one of those species shows a consistent trend of sort of effectively a decrease in their creation rate as you go to higher and higher energy cosmic rays, which is basically saying that the high energy cosmic rays spent less time traversing the ISM column, basically. They had fewer encounters along the way. So that's the biggest piece of it, is that they all qualitatively go that way. And the debate is largely about, in the literature, exactly what the power law slope of the dependence is. Is it 0.5, is it 0.4, is it 0.6? But it's at that level or something. But yeah. There's some other indirect arguments from gamma ray spectra and things like that as well.
Okay, so let's thank Phil again.
Get out of the way. Sorry, I'm going to sneak through this way.
So next speaker is Frederic Bournaud, who will talk about clamps and contractions.
Seems to work, and thank you, Phil, for your previous talk. And so I'll talk a little bit about galaxy morphology, the relation between galaxy morphology and feedback and the abstraction. How many of variants in the form of gas and diffuse gas and stars, which is what we call the gas fraction and associated feedback. Star formation and cosmic ray feedback. So as we all know, there is feedback from supernovae explosion and associated supernovae feedback along and cosmic ray feedback along the cosmic field, and as a function of the coefficient diffusion. And we are doing some idealized simulation which are led by Marion Farsi, which is a student in Lyon with Jérémy Blaiseau, Yuki Rosdahl, which you all know here. Most of you know here as a function of galaxy mass. And she is showing that cosmic ray feedback and the way cosmic rays are hitting diffuse gas clouds, this is the column density here, is important with respect to star formation efficiency. Because to get star formation, you need dense gas and cosmic rays from young star generations that are expelled from the spiral arms along the so-called spurs. As you see here, perpendicular to spiral arms, and that, as we'll see later, are expelled from the spiral arms, but this is observed, reduce the gas density and limit the star formation without necessarily supernova explosion, just with turbulence and radiation. So these are two versions of the same simulation from idealized simulation of a Milky Way-like galaxy at 22, so a bit below, a factor 3 below the mass of the Milky Way, without cosmic rays and with cosmic rays. And you do see that the disk synergon here is more turbulent with cosmic rays. So I think we do agree with Phil's previous talk that cosmic rays are not the full solution. Cosmic rays are part of the solution. They do participate to the regulation of star formation. Star formation is still too high here if you do not boost the feedback factor. So there is still something that we do not understand because the star formation rate here is still a bit above if you look at the values, the Schmidt-Kennicut logo. Basically, this is shown here. This is the time from the Big Bang. The stellar mass of a galaxy, what it should be analytically, what it is with cosmic wave feedback, what it is without cosmic wave feedback. So cosmic waves are helping, but they do not solve the problem. And that's the idea of the message. And yet we do have a cold ISM phase, but not enough gas is dense enough to cool enough to fall in the ISM phase. And the gas is still too warm, mostly, like if it were without cosmic wave feedback. This is the case for most of the gas. And then it doesn't cool. And if it doesn't cool, it's from stars. So the star formation rate is too low, and the cooling rate is too low, and the gas is too warm. This is what we have. The paper is on AstroPH from the Felipe Senal simulations here. So this is the MG2 covering fraction, and this is what is observed. Well, this is a fit observation. There's still a factor 10 in time, well, in size, but in expansion. Too much between simulations and observations. So it still seems I think this is a major issue for all of us to think about in the next years. That cooling is too limited to very dense gas locally in small-scale structures. That is here in simulations, where it should be here, a factor 10 larger in simulations. So now let's come to the clumps and the high-redshift galaxy instability, which is a dear topic for Avishai and many of you here. So I think we all agree that the gas fraction here, as a function of redshift here, increases so that galaxies between redshift 2 and 1 have about 50% of gas in their baryonic matter. It's not from CO, it's not from dust, it's not from many observables. They all converge toward the same result, which is like 50% of gas among the baryons in galaxies at redshift 2. Many groups have established this. And it seems that as a result, when you look at galaxies the size of the Milky Way and the mass of the Milky Way at redshift 1 or 2, you see these kind of homologies that are very irregular with big clumps of star formation. Okay, these are red-shifted, blue-shifted observations because you are looking at the light emitted in UV, but it means that the star formation is dominated by a few big clumps of star formation. And here, these are what nearby galaxies would look like M33 or M81, if they were observed at redshift 1 by the HST. This is what galaxies between redshift 1 and 2 look like when they are actually observed by the HST. So they are much more clumpy, irregular, even if there are hints of spiralams. And there have been quantitative analyses. Well, some of you here in the room know this, but this is Murata 2013. The function of regular barred galaxies as a function of redshift, the x-axis is the redshift, and the function of clumpy irregular galaxies. This has been questioned recently on two bases. One basis is the imaging on lensed galaxies by the HST. So you look at a galaxy as if basically as if the angular resolution was higher because of the lensing effect. And what you see is Daniel Scherer, Mirolasa Desauge, and company have shown this. You don't see a few big clumps, you see many tiny clumps. This is in blue what they find with the lensing imaging. With ALMA is the same. You see many small clumps. And more recently, I'm sorry if someone is in the room, but I don't have the exact reference, but with DWS30, in lensed DWS data, you see a few small clumps as if it was a spiral galaxy today. But this is something we published a year ago with 4 et al. And Emmanuel Edadi, showing this is a galaxy, the mass center is here. This is more or less the F-mass radius here. And we do see many small blobs. But if you were looking at the galaxy with the HSC resolution, this is what you would see. You would see 1, 2, 3, 4, 5, 6, 5 or 6 big blobs. Because the conglomerates of small blobs are gravitationally bound. Even those ones, all those ones, if you make the measurement, they are gravitationally bound here. So this is what we might call a clump. And it corresponds, it's not exactly the same time frame, but it corresponds to these ones. So it's possible that we don't see big clumps of star formation just because they are resolved due to the very high resolution of modern instruments, or because of the help of gravitational lensing, or a combination of both of them. Now I want to comment on cosmological simulations, and I'll be a bit provocative, but I think this is aimed at triggering the discussion. When you look at galaxies in Fire or Fire 2 simulations, there are very nice spirals, very nice dust lights. None of them has a bar. But no one is doing better. I think we have to admit that no one is doing better. It's the same in Illustrates. In Illustrates, the equal 0 disks that are selected to be on the star formation main sequence, so galaxies that are forming stars. I don't really see bars. Well, okay, there's 1, maybe 2. But when you look at observations, 80% of star-forming galaxies should have bars, which is a framework of the dynamical status of those disks. When you look at non-star-forming galaxies, at which is 0 in Illustrates, most of them have bars. It's about, it's about. Ain't it? Most of them have bars. And I think that's a critical issue. Just on this picture, just look at the, forget the orange points, just look at the green ones. This is the bar fraction as a function of redshift. Above redshift 1, there's no barred galaxy. Below redshift 1, there should be a barred galaxy. And present-day cosmological simulation are saying sort of the opposite. So I think this is a challenge. I think this is related to gas fraction in simulated galaxies. So let me show you, these are 2 galaxies more or less the same potential well. They lie in the same potential well. This one has a 19% gas fraction. So it has a lot of stars on the little back gas fraction. This one has the same total mass distribution, but it has 60% of gas on the lower stellar mass. Let's see how both of them evolve. Of course, they are not the truth. They are outside of the cosmological context. But let's see how they evolve. This is the gas poor galaxy. Okay. It's a nice spiral. Sometimes there are big blobs along the parallels. And the spiral share the blobs away. So let's look at the same galaxy with the same total mass, the same rotation curve. Just a higher amount of collisionless material. Let me show you again the low gas fraction version. Oh, there's a nice blob here. But it's shared away. I wanted it to survive, but it's shared away. Let's look again at the high gas fraction version. All right? Like here, there's a nice gas blob. It remains forever. I've been checking because this version has a low efficiency stellar feedback. It was only thermal feedback. And as you know, if we implement in numerical simulation supernova feedback as just thermal, it rapidly cools away. That one with a high gas fraction has thermal plus kinetic plus H2 feedback plus radiation pressure. Very efficient feedback. So we should have disrupted, if feedback was the cause of feedback disruption, it should have happened on this case. Let's look again. Feedback is very strong here. Feedback is weak here, only thermal supernova feedback. You have spiral arms that are disrupted by shear here. You have giant clumps here. So I'm just posing the question because I don't mean any of our models is the truth. But I think there is something to explore in the competition between feedback, cooling, and dissipation, kinetic dissipation of turbulence. Something interesting, I think, is the loading factor of outflows. So this is this factor, which is the amount of mass that galaxies are losing through outflows, now less to the amount of mass that galaxies are consuming into star formation. This is like a factor 10 to 30. Well, it depends on galaxy mass and redshift, but if you want to take a Milky Way progenitor at redshift 2 in Illustris, it's a factor 10, which means that there are 10 times more gas expelled from the galaxy that gas converting into stars. I think fire is more or less saying the same. But we can discuss this. I think this is a bit contradictory with observations. These are observations by the Genzel-Team, where the same loading factor is about 1/3 So the mass of gas expelled from star-forming galaxies is 1/3 compared to the rate of gas to start conversion, so the rate of gas that will forever remain into galaxies in the form of stars. This is more or less the same in the observations by Blaiseau, Boucher, Schroeter, and company. They are observing gas further away from galaxy as observers in front of background quasars. And they say it's about 1/3. So I think this is well, I should show you very nice loading factors from Avishai, Daniel Severino, Sandro Takela, from the Vela simulations. The loading factors eta, which are the ratio of star formation rate above mass growth rate, are about of the order of unity, which seems to be consistent with the observations. And the gas fractions, about redshift 1 or 2, seem to be, well, they are a bit below unity, but they are not so far. I mean, in agreement with what observers says, they seems to be, I should say, the best observations, the best simulations so far. The question is why? And then why does the question is why does moderate feedback with a loading factor of outflows just of the order of unity provide galaxy gas fractions about 40–50% at redshift 1, 2?
No, 5 minutes.
I'm none.
Okay.
I'm fine. We can start the discussion. I'm happy to trigger the discussion.
Thank you, Frederic. Anyone wants to comment on this? Well, Santi, you're here.
It's just about the topic of bars. I am, in fact, not surprised that you cannot generate bars in the cosmological models, basically because the bars in young disks, in very cold disks, are quite sensitive to resolution. You are not resolving many scale heights for these disks still in these cosmological simulations. So it's difficult to really simulate the orbits that will generate the bars in a secular way. But on the other hand, you are simulating very well the production of bars that are results of the mergers, that are very different. These bars, these old bars that you observe in the quenched galaxies, are different from the ones you expect for cold disks. So I am, in fact, not very surprised, and I really think that this is a matter of...
So wait, you went bar the galaxies?
Yeah, for the bar.
Yeah. Okay. No, just go ahead. I wasn't sure I understood correctly.
So I don't actually think this contradicts the general point you were making, but I just wanted to clarify, because I think it's come up a couple times, that there are several fire galaxies that have very strong bars. In fact, of the original 3 Latte simulations that Andrew Wetzel ran, one of them had a very strong bar that buckles and forms a bulge, and Victor de Batista wrote a paper in 2019 that's a case study of the bar dynamics and the vertex deviation of the pseudo-bulge that it forms.
Okay.
And Robin Sanderson's shown some similar things. I think the quantitative comparison for us is very tricky with our small statistics. I do think it's an example, though, where we need to be careful about, if you want to start comparing those quantitatively, how observers define a bar applied to the simulations consistently. And yeah, I'm glad to see people pushing to do that.
Well,
Comments? Yeah.
I would like to respond because I think it's important.
You have the mic. You can talk.
Oh, does anyone? Okay, so I can talk. I think you're right, Phil. My talk was a bit provocative because we want to discuss. And I think making barred galaxies at Redshift 0 remains a challenge. But I'm happy to hear that that you may be solving it.
There's some. I wouldn't even say. I wouldn't.
Yeah. But
whether it's
yeah.
actually the right number, and
Yeah.
I think your point is good though too about are they in the right galaxies, right?
Yes, because I think while there are papers by Thorsten Naab and other colleagues saying that we can make barred galaxies in red galaxies, on the red sequence, non-star forming galaxies. I think, well, this is from 10 years ago. 10 years ago, we had many in cosmological simulations of galaxy formations. We have barred galaxies that were in non-star forming galaxies, red galaxies, and the blue galaxies were unbarred. And we want to go beyond this. And I agree that you have some good examples in your recent papers. I think this is still a good test for our statistics. For yours, for mine, for everyone's.
I like a couple of points that you make. I just wanted to make sure that we all understand what are the mass loadings in fire. So the values of 10 or 20 that people sometimes quote are actually for dwarf galaxies. And if you go to the plot you showed, those are for like 50, 60 kilometers per second halos. For the massive halos, for observations, our mass loadings are around 2 at high redshift and close to 0 at low redshift. So I don't think they're that much different than the other values. And the second thing is observational mass loading measurement is tricky business because
For sure it is.
you are seeing what star formation is doing now and you're measuring something in CGM that might have been ejected at earlier times.
Yeah.
So, I mean, we should definitely keep comparing stuff, but I don't think our values are that much higher. There might be a factor of 2 higher than what you're showing here.
Okay, I agree.
Comments? Question?
Not much to add, but I agree with your comment. As I told earlier, there are so many uncertainties on these measurements. I agree.
Sorry, just let me complement a bit what I was telling before. It's true that there are many models that cosmological models that already produced bars. Also, back in 2016, 2014, many people with zoom-in simulations at resolution of 40 parsecs, they produced very good and strong bars. But there is also another parameter that we quite commonly use for isolated models, that is the ratio between the disk mass and the halo mass. That basically this allows you to produce a simulation with a strong bar or without bar, just changing this ratio, because basically you need a transfer of angular momentum between the disk and the halo. So maybe looking at these galaxies that produce strong bars in fire and in Illustris, you will just find out that you're producing strong bars in the models in where it's easier to produce them because the transfer of angular momentum is high. But in the other ones, it's you cannot because there is no enough transfer. No, I don't know. It's just
the idea can work theoretically. There's no observational support to this for so much enriched baryons to be in the outflows so far. But you might be wrong. You might be right. Sorry. Well, you might be wrong. You might be wrong.
Both words.
I may be wrong, and you may be right. I think there's not enough precision of the enrichment data. And your scenario is as likely as any other scenario. That's my take.
Is there any other question for Fred? Comment? Okay, thanks again.